Light is an amazing thing once you fully understand it. It can get kind of complicated. So what we're going to start with in this lesson is thinking about light as a wave. Maybe you've heard of this before, and light does act like a wave, but it also acts like a particle called a photon. We'll get to the photon in the next lesson, and then we'll kind of merge the two things together. For this one, let's focus on when light acts like a wave. First of all, what is light? We talked about this briefly in the last lesson. If you haven't watched that, there's links down in the description to keep you on track here. But the whole point here is that light is a general term for the electromagnetic spectrum that we see with our eyes. And where does that electromagnetic spectrum come from? Well, that's electrons jumping up and falling back down and giving off energy. Okay? So electromagnetic radiation, which is light or visible light is a part of that, is a wave of energy with a specific wavelength and frequency. We should probably know what wavelength and frequency are before we move too far forward. And another important thing, light always travels at the same speed. That's 3.00 times 10 to the 8th meters per second. Those are the numbers we're going to use throughout these lessons. I would put this information in my notes if I was taking notes, because we're going to do some measurements off this over the next several lessons. Parts of a wave, amplitude isn't a big deal for us for these lessons, but wavelength is a big deal, and that's a measurement from crest to crest or trough to trough. First one is wavelength. So this symbol represents wavelength. We need to remember that because we'll need it for a long time. Now, I teach my students, if I look at this here, I sort of think this looks like a wave curling over, and this is you surfing that wave. There's your surfboard. You're like, hang 10. I don't know. But we're going to get lots of symbols as we learn chemistry. And for me, this one right here sort of looks like a wave. So we're going to call that wavelength. By definition, wavelength is the shortest distance between equivalent points, like from crest to crest, or you can measure down here from trough to trough. And it is expressed in meters or some form of meters like nanometers or kilometers or decimeters. And the wavelength determines the color of light. The next key concept is frequency. The symbol for frequency is this, well, in English, letter V. So what I tell my students is from now on, we're going to call this the frequency so we can remember that the V represents the frequency. Again, throughout the course of introductory chemistry, you end up with a lot of symbols. So this one, the way we remember it in my class, is frequency. Frequency is the number of waves that pass a given point per second. We use hertz to describe that, and 1 hertz literally means 1 wave per second. 2 hertz would be 2 waves per second. 10 hertz would be 10 waves per second. If we counted 100 waves per second, that would be how many hertz? 100 hertz. There are ways of labeling this. Hz for hertz, or 1 over seconds. So let me show you. 1 over s is another way of expressing hertz. But in math terms, you'll oftentimes see it written this way, which s over 1 is the same thing as 1 over s. Those mean the same thing, which is hertz. So all of these are interrelated. Let's see if we can find a relationship between wavelength and frequency when it comes to light. Remember, wavelength is this symbol, and frequency is the frequency over here. We have our 2 symbols. And I'm just going to use, this is a very poor drawing, I apologize, of the beach. This is you looking at the beach from the side. There is you hanging out on the beach, and so we're just looking, and let me try to make a little more sense of this. Oh, there we go. Now this has a certain wavelength that we could measure, but how do we deal with frequency? Well, let's start a stopwatch for 1 second. And then we're standing here and we're going to count how many of those waves come and reach the beach in 1 second. So here we go. I'm going to start. Boop. 1, 2, 3. Boop. 3 waves reach the beach. I'm making that up. But if 3 waves reach the beach, that's 3 hertz. Now, none of that makes sense until we do this. Let me switch the color. Let's put a blue wave on here to compare. There's our blue wave. Now, what do we notice is different about the blue wave that's coming towards us? The wavelength is shorter than that first wave we looked at. So let's go ahead and start our stopwatch, and we're going to set it for 1 second because hertz is how many waves reach our little beach here in 1 second. And so, boop, 2, 3, 4, 5, 6, 10 waves reached the beach. So 10 of them came, because remember, they're all moving at the speed of light, but now the wavelength is shorter, so more of them are going to hit the beach in that 1 second. So what happened to the frequency? It increased. As the wavelength went down, the frequency went up. Let's draw in a red wave over the top of these. Whoa, look at our red wave. Has a really, really long wavelength. Really long wavelength. Now, this wave is coming towards the beach at the speed of light, 3.00 times 10 to the 8th meter per second. We start our timer for 1 second. Boop, boop. Only one wave reached the beach in 1 second, which means the frequency went down. Notice, when wavelength goes down, frequency goes up. When wavelength goes up, frequency goes down. These two are related mathematically. This relationship is inverse. As wavelength goes up, frequency goes down. As wavelength goes down, frequency goes up. So there must be a formula then that relates these things. And before I jump into that, now look, blue light, when you see blue light, you're seeing something that has a shorter wavelength. That's why I drew it shorter. Red light has a really long wavelength. And then the other colors that we see fall in between. Your eye distinguishes that because, well, the frequency of the light that's hitting your eye or your receptors in your eye tells it what color it should tell your brain you're seeing at that moment. Because there is a relationship, we can look at this mathematically. Now, whenever I'm teaching a lesson and I put a box around something that I think should be in your notes, that's something that you're going to need for all of introductory chemistry or all of Chem 1. So this has a box around it. This is something that we're going to need all the time. Here's our formula. C equals the wavelength, remember that symbol, times the frequency. C is the speed of light. We know that. We remember it's 3.00 times 10 to the 8th meters per second. Put that down on your put that in your notes because you're going to need that for all of the lessons that we're going to cover. Wavelength, we talked about that, is measured in meters or some form of meters, like maybe nanometers or kilometers. And then the frequency over here is measured in hertz. So here we go. Let's put that equation to the test. Notice we have what is the frequency of green light, which has a wavelength of 4.90 times 10 to the negative 7 meters. We only have one formula so far, so this is going to be fairly easy. We have C equals the wavelength times the frequency. Do we know C? Yes, it's constant. It is 3.00 times 10 to the 8th meters per second, and that's equal to the wavelength, which is 4.90 times 10 to the negative 7th meters times the frequency. Now, we need to rearrange this to solve for just the frequency. How do we do that? We divide both sides, 4.90 times 10 to the negative 7 meters. Divide both sides by this, 4.90 times 10 to the negative 7 meters. These are going to cancel, right? So let me clean this up. And then I just plug it into my calculator, which means the frequency is 6.12 times 10 to the 14th. Now, what are my units? Let's see here. I have meters on the bottom and I have meters on the top. And the only thing I'm left with is per second. Well, that's fine because per second is hertz, right? So I'll just write hertz here, and that is the frequency of this light. Now think about that. When you see green light coming in towards your eyes, it's hitting the waves or the different, they're hitting the photoreceptors in your eye 6.12 times 10 to the 14 times per second. That's pretty wild to think about. At this point, this is where I would tell you to pause the video and work through this problem on your own and see how you do, and then play the video and watch me work through it. The best way to learn is by you doing things on your own and then checking your answer. So we've got a radio station. It's called Hot 101.9, and it broadcasts a radio frequency, that looks like an important word, of 101.9 MHz, which is megahertz. Oh, look, here's some information about megahertz. What is the wavelength of the broadcast? So I need some sort of relationship between light, wavelength, and frequency. We know that formula. That's the one we just used. C equals the wavelength times the frequency. Let's fill in our variables here. We know C. It never changes. It's 3.00 times 10 to the 8th meters per second. That's equal to the wavelength. Now, we don't know the wavelength. We're going to try to solve for that, so I'll leave it this way, times the frequency. But the frequency is in megahertz. And we said earlier we need to have it in hertz. So I need to do some converting here. And this is where dimensional analysis comes in. If you don't remember dimensional analysis, well, I'll put a link down in the description and you go refresh your memory on dimensional analysis. We write down what we know, which is 101.9 MHz, megahertz. And I'm trying to turn that into hertz. So this is reminding me of where I'm trying to get to. I need a conversion factor with megahertz down here because that's the only way to cancel that out is to have it on opposite sides of the line. And can I turn megahertz into hertz? It does look like there's a relationship right here. 1 megahertz equals 1 times 10 to the 6th hertz. Let me cancel a few things out. Those cancel. Oh, look, only thing I have left is hertz. Now I just plug it into the calculator. And I get 1.019 times 10 to the 8th hertz. Where does that go? Well, that's going to go right up here for our frequency. 1.019 times 10 to the 8th hertz. Sorry, I need to fix that. Then I just rearrange to solve for the wavelength, and I'm all good. We're going to divide both sides by 1.019 times 10 to the 8th hertz. We do that with both sides, 1.019 times 10 to the 8th hertz. These are going to cancel. Plug it into my calculator, and I get 2.94. Now let's see about units. Hertz is per second, right? Per second. Well, look, there's a per second there and a per second there. I'm left with meters, so this is meters. Now think about this. The one we looked at before had this tiny, tiny wavelength. Now this radio wave has a massive wavelength, almost 3 meters long. And just so you know, I'm using the correct number of significant digits in my answer down here. If you don't understand significant digits, check out my earlier lessons that'll show you how to deal with all of this math. So there's our introduction to light as a wave and how to calculate frequency and how to calculate wavelength. But the thing is, if we go back 2 lessons and we were looking at all the different colors that were coming off of an atom as electrons were jumping up and falling back down, these 2 things are related. As the electron is doing that, it's giving off different wavelengths of light. Different waves of light give us different colors, which gives us the entire spectrum, all the colors that we can see and all the colors that we can't see. And then if you want to learn more things, come over to bealsscienceschool.com or see experiments at bealsscience.com. And I hope with all of this stuff, it reminds you to keep on learning.